So you put an ice cube in a cup of coffee, a styrofoam cup. You would very probably be surprised if the ice cube got colder and the coffee got hotter. We'd all be surprised. Would this violate the energy principle?
If it got colder and got warmer.
No, if the ice cube gets colder and the coffee gets hotter.
So would that?
Yes, would that violate the energy principle? Okay, so who thinks it would violate the energy principle? Who thinks it wouldn't violate the energy principle? You're right, it wouldn't violate the energy principle. So, depending on what you pick, let's pick the system as the ice cube plus the coffee. Okay, there's nothing in the surroundings doing mechanical work on this system, right? So it's in a styrofoam cup, so it's pretty well insulated from the air. That's 0. So the change in energy of the system is 0, as long as so we know that the change in internal energy of the ice, the change in internal energy of the coffee has to add up to 0, but does this tell us which way it has to go? It actually doesn't. Now we actually are pretty convinced that that's not going to happen, but it's not because of the energy principle. So I put a piece of chalk on the table. And atoms in the table are vibrating, we know that. So they're colliding with the chalk, right? So if I wait long enough, couldn't it happen that all the atoms are moving right under the chalk, are moving up at the same time, and the chalk jumps up in the air?
That'd be cool.
It would be surprising. But does it violate anything? So momentum from the atoms in the table to the chalk. Change in momentum of the chalk plus change in momentum of the surroundings could be 0. Chalk could jump up in the air. How long do you think I'd have to wait to see that happen? A really long time. A really long time. So there's something about these phenomena despite the power of the fundamental principles we have, that actually doesn't tell us exactly what direction things are gonna go. If we drop a ball, a tennis ball, and it bounces on the table, typically it gets lower and lower and lower and lower and stops. We'd be a little surprised if it got higher and higher and higher and higher. But there's really nothing fundamental in these principles that tells us that can't happen. So what we're interested in this final chapter, this chapter 12, is talking about processes that are irreversible, processes that go forward but not backward, processes that go in one direction but not another, and why that happens. And it turns out that what we're actually going to be talking about is randomness and probability, the randomness of events at the microscopic level. And that's going to lead us to a discussion of entropy and where entropy comes from. And this may be a little bit different from the way you've talked about entropy in other classes. So, and we're going to deal with situations like what happens to the temperature of the ice or the temperature of the coffee. We're going to deal with situations like why we don't actually see the pen jumping up, the chalk jumping up in the air. And think about it just from the viewpoint of randomness and probability, fundamentally how that works. So here is somewhere here is, yes, a VPython program that shows, what is this? It's a very simplified model of a gas. So gas molecules bounce around, traveling in all directions in 3D and collide with each other and move around pretty much in random directions as a function of collisions, right? This is a simplified model. First, it's 2D. And second, instead of letting them move anywhere, what we're doing is saying, well, they're going to move randomly on a grid, which is called a lattice. And there's a whole class of computational models called lattice models where you simplify completely unconstrained random motion by just constraining motion to. So what each of these particles is going to do is going to take one step in some random direction on this grid. It can go up, to the right, down, or to the left, and if there's something there, it can't do it. And if there's a wall, it can't do it. And we're going to put these particles here, and we're going to let them go. So now they're all taking these random steps on the grid, and that's all that's happening. There's nothing else going on in this program. Every time through the loop, every particle tries to take a random step. If it's colliding with something, it doesn't do it. That's the same as moving and bouncing back. And eventually it sort of seems kind of spread out. Now, in principle, they could all just end up going back to the lower left corner, right? How likely is that? So not very probable, but it's not out of the question. It's just that there's so many other things they can do that getting to that configuration is actually one of a huge number of possible things that could happen, and there's a very small probability of it actually happening. Now so this was basically diffusion, right? So we put a drop of perfume, here, and eventually it diffuses out through the room, and eventually the people in the back row can actually smell it. Okay. Now, in principle, it could all diffuse back here, but it's just there's no force driving it. It's just happening through randomness. Now there's another, whoops. We can think about something else here, which is suppose so that got to a point where things look kind of uniform, right? In a certain sense. Let's try to quantify that by putting some counters in here. So what these are going to do, these little boxes here, are just going to measure the density of the particles inside each box at every moment. Okay? And then they're gonna graph it. And I'm going to make this small enough that we can actually see the graph. So here we've, I have to make it a little bit smaller. So moving around, the blue line is the density of particles inside the blue rectangle, and the red line is the density of particles inside the red rectangle, and they're made different sizes for no particular reason, because its density is number divided by area, right, in this case. So eventually, it looks like we're getting to a situation where the densities are about the same. And if we speed it up, I should have made the rate faster. Let's make the rate faster. It might be, whoops. Let's give it a much faster rate. Make it big enough that I can read the code. Okay. Okay, so if we look at our graph of density here, we see that the densities have equilibrated to be pretty much the same, but not quite exactly always, because there are fluctuations. And since we don't, at the macroscopic level, if we measured density, we'd be getting the same densities. At the microscopic level, there's fluctuations. And it's particularly noticeable because we have such a small number of particles. Now, if we had 10 to the 23rd particles in our simulation, and if we had a computer big macho enough to run that in real time, then these fluctuations would look really small compared to the density. So even in this state, which we can call equilibrium, there are fluctuations. I thought it was supposed to keep running, but okay. There are fluctuations just due to randomness. And so something that looks smooth isn't really quite smooth. Okay, so we've talked about energy exchange between solid objects. So we talked about putting a cube of aluminum or something at some initial temperature what do we do? At 50 Celsius next to a cube of iron at 100 Celsius and bringing them together, and we figure out what the temperature would be based on the energy principle, because internal energy leaving one goes into the other, okay? But even in that system, there can be some fluctuations. So when these blocks are close together, we figured out the eventual final temperature, and we figured out the change of internal energy of this and that to get there. But even in this final equilibrium state, you know, occasionally the block could have a little less energy than we expect, or it could go the other way. So there's still these microscopic fluctuations going on. And so what we're interested in this final piece of the course is using what we know about energy in solids to actually understand from a microscopic view how we get to this final equilibrium state, and along the way through random events, and along the way trying to get a much more precise physics-y definition of temperature, which we've sort of waved our hands and said had something to do with the amount of internal energy in something. And finally, to talk about heat capacity, which we used in calculating this, and to see where that actually comes from. And we're going to do it just starting from simple physics that we already know, and acknowledging that events at the microscopic level are, and so we have to use a little bit of probability. So that's what we're going to be doing. Now, let me remind you that okay. So remember that we have this model of a solid that's balls connected by springs, and maybe we want to find that. So here's so here is our model of a solid. The balls are the massive atomic nuclei and the inner electrons, and the springs are the covalent bonds between them. And the internal energy of a solid is just the energy, the kinetic energy of the atoms and the potential energy of these compressed and stretched springs. And then recently, we talked about the fact that for a microscopic system, so a microscopic oscillator, we know that the potential energy function for a spring is a parabola, and we know that for two atoms bonded to each other, even though the potential energy function is better represented something like this, where this is energy, and this is the distance between the atoms. So the distance between the atoms. That the bottom of this well is pretty parabolic, and so until we get things to some super high excited state, pretty much we're talking about ideal oscillators, and that the energy of such a system is quantized, meaning it can only have certain values. The lowest possible value, called the ground state, and that corresponds to a low energy, which really corresponds to a low amplitude of vibration. And in fact, in this potential energy, if we talk about for a minute an ideal spring here, this parabolic well, this is the equilibrium distance. So it's compressed or expanded here. So this is R, this is energy. When k plus u, so this is some value of k plus u, when R has this value, something's at its maximum stretch, and so all of the energy is in the spring energy. There's no kinetic energy. And this distance is in fact just the amplitude of the vibration. It's just going from there to there. So at that point the energy is a half k sub s squared, but s is equal to a, so it's just a half k sub s a squared. That's and if we put in more energy, we have to do it in steps of, the step is a step of delta E, which is equal to h bar omega, where h bar is a constant, 1.05 times 10 to the minus 34, I think, joule second. Yep. And omega is that thing we derived using the the derivative form of the momentum principle, where it was spring stiffness over the mass. But in this case, for all the interatomic spring stiffness, and this is the mass of one atom. Okay, so we can calculate the energy difference, and all these spacings are the same here. All these which makes a solid sort of easy to do calculations with at this level. And so more energy just means a higher amplitude. Okay, now it's the case though that in a solid any given atom can vibrate in 3 dimensions. So there's X, Y, and Z, right? Especially in our model solid that has a cubical lattice. And so we should be able to put energy into different directions of vibration. So if this is X, let's make this a little, and I put a lot of energy into the X component of the vibration, we excite that vibrational mode. Or if I put it into the Y vibration, we get a lot of vibration in the Y direction, or Z, out Z. Z, it doesn't want me to, there we go. Z is toward us, yeah. Okay, so there are really three possible directions for this vibration. Now, we're going to simplify this a little bit further by using a model that actually Albert Einstein invented. So this is called the Einstein model of a solid, and he invented it to talk about these issues. We say that instead of noting, like in this particular case here, noting that if something has a lot of excitation in the Y direction, it's actually changing Z springs also. And furthermore, we know that there's another atom over here that's vibrating that's going to affect that. We say we're going to model this solid as if it was made up of completely independent oscillators, so that one atom, the motion of one atom doesn't affect another atom. So independent oscillators and in fact, we're going to say every atom we can model by 3 completely independent oscillators, one for X, one for Y, and one for Z. So one atom goes to 3 oscillators. So we have these 3 independent potential energy wells and 3 of K plus U. And there's even kind of a, this isn't completely insane in terms of physics here. So what we're saying is that this one atom goes to three oscillators. This even makes some physics sense, because the energy is going to be, of this oscillator, is going to be K plus U. So this is going to be equal to p squared over 2m for the atom. And this is going to be a half k sub s squared. We can write this as, since the magnitude of p is the square root of p sub x squared plus p sub y squared plus p sub z squared over 2m here. And so we take the square root and then we square it. So p squared is just p sub x squared. Magnitude of p squared is p sub x squared plus p sub y squared plus p sub z squared. We write s as actually a vector. So it's the stretch times the direction of the stretch. Then we'd get a half k sub s times sx squared plus sy squared plus sz squared. And if we just rearrange the terms, this really does look like three independent oscillators. So we have px squared over 2m plus a half k sub s sx squared plus the y terms plus the z terms. So in fact, it's not physically unreasonable to, yeah.
So in the equation, we have sx squared plus sy squared plus sz, everything to the square. That would be right?
Right, no square. Thank you. The 2 leaked out. Okay, so this is our model of a solid, and we're going to say that that we have all these atoms in our lattice, and we're going to model each atom as 3 separate oscillators, one in x and y and z. So x, y, z. And since they're not effective, well, they can always emit photons, and something else could absorb photons. So that could be how it's happening. Okay. So what we're going to do here is think about what we can do with this model. And we're going to talk about, given a certain amount of energy, how many ways are there to arrange it in among all the oscillators we've got. So here's a block of metal, and we're going to talk about nanoparticles of metal, so we can do this stuff on our calculators or with a computer, but it scales up to a big block. So here's a block of metal. There's a certain amount of energy in it. What's the most, how many ways are there to arrange the energy? And what we're heading toward is being able to predict from this microscopic analysis what the partition of energy is going to be between 2 objects that get put together. The most probable partition, the partition we see. And why does the most probable mean that we're really extremely unlikely to see anything else at equilibrium? So that's the goal here. So let's talk about one atom. So we have one atom is 3 oscillators. So we have And let's say we have two quanta of energy. What does that mean? It means we have 2 times this delta E, which is 2 times h bar. The textbook calls it omega sub 0. Okay, we're just going to write omega here, but where this is 2 times h bar times the square root of the interatomic spring stiffness over the mass of an atom. How many different ways can we arrange these 2 quanta among these 3 oscillators? Well, here's one way. And 2 quanta means above the ground state. Okay, so you can never go below the ground state. So 2 quanta, we mean above the ground state. So we could put 2 quanta in here, and none here, none here. So we'll call that 2, 0, 0. And that's one way of arranging those 2 quanta among those 3 oscillators in this atom. And we could also do we could put 2 here, and we'd have 0, and it's going to get really tiresome to draw pictures, so let's not draw any more pictures. So we could have 0, 2, 0. We could have 0 here, 0 here, and 2 here. We could have 1 here, and 1 here, and none here. We could have 1 here, and none here, and 1 here. We could have 0, 1, 1. Is there anything else? That's it, right? So there are 1, 2, 3, 4, 5, 6 ways to arrange 2 quanta of energy. In 3 oscillators. And the important piece of this leads us to what we're going to call the fundamental assumption of statistical mechanics. This topic is the intro to what's called statistical mechanics, which is the fundamental assumption of statistical mechanics is that each of these ways of arranging energy is equally probable. So if we took a time-lapse, we set up a camera to take time-lapse photos of this system, and we took a photo every second. And in between, photons are being emitted and absorbed randomly. What that says is that if we took 600 photos, we'd find that about 100 of them look like this, and 100 look like this, and 100 look like this. Okay, so equally probable. Now, there's a technical name for these ways of arranging energy. Each way of arranging energy is called a microstate. So these are microstates. And what's a macrostate? Well, the macrostate is that for our system of 3 oscillators, there's 2 quanta of energy to be distributed. So this is our macrostate. And it's that every microstate corresponding to a given macrostate is equally probable. Or in less fancy words, every way of arranging energy, the available energy in a given system is equally probable. Okay. So So let's see if we can do this for a slightly bigger, a system with slightly more energy. We have one atom, so 3 oscillators, but now we have 4 quanta of energy. So list, using this kind of notation, list all the ways you can find to arrange these 4 quanta of energy among these 3 oscillators. And let's figure out how many ways there are. So what I'm talking about is just writing down all these configurations and then counting them. So you need a minute, or have you got it? So why are we doing this? We're doing this because we're leading up to thinking about arranging energy between 2 in thermal contact. So, okay, so what'd you get? Okay, so I'm seeing 4s, seeing 3s. Okay, I'm seeing 3s and 4s, so we don't completely agree. So let's see what we've got. We have 4 0 0 0 4 0 0 0 4, right? We have 3 1 0 3 0 1 0 3 1 0 1 3 0 1 0 3 0, 1, 3. And now we have 2's. We have 2, 2, 0, 2, 0, 2, 0, 2, 2, 2, 1, 1, 1, 2, 1, 1, 1, 2. That might be it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 4 is the correct answer. There are 15 ways, 15 ways to do it. So there's because ways to arrange energy is a long phrase, we give it a symbol. The symbol is a capital Greek omega. Not to be confused with the lowercase omega, which was an angular frequency. It's the number of ways of arranging energy. Okay, this could get old real fast. We need an equation, right? So we need to be able just to calculate it. And it turns out that there is a formula that comes from probability, has to do with combinations, that works out here. And the equation is that the number of ways arrange, if we have Q quanta of energy, so the number of quanta of energy is Q, we have n oscillators. Is equal to Q plus n minus 1 factorial over Q factorial times n minus 1 factorial. So let's just see if it works, and then we'll worry about where it came from. What?
Is it a good thing or recently?
Factorial. Factorial. 5 factorial is 5 times 4 times 3 times... Okay, so let's see if this actually works, and then we'll... Yes?
Isn't this summation rule?
What?
Is this like not part of selection rule?
Not what?
Is that part of selection rule?
No, this is a combinations formula from probability. The combinations of it's sometimes said as the combinations of n things taken m at a time or something like this. And we'll see where that comes from in a sec. So let's just do it here. This would give us, so how many, what is Q in this case? 4. We had 3 oscillators. Divided by 4 factorial times 3 minus 1 factorial. That gives us 4 plus 3 is 6. 6 factorial over 4 factorial times 2 factorial. And so that's 6 times 5 times 4 times 3 times 1 divided by 4 times 3 times 1 times 2 times 1. And to simplify our lives, we can cancel some things. So cancel that out, which gives us 30 over 2, which gives us 15, so it comes out right. Now on your calculators, you'll find factorial functions, and that may be adequate. But there's also this whole thing exists as a function in VPython called combin. So in VPython it's going to be combin of A and B. And that it probably exists. This exists on your calculator too. It often is written as NCR or something like that. Depending on what you have a calculator, an 83, TI 83 or an 89 or I don't know what. I mean, okay. So where does this come from? It comes from some sort of fundamental probability formulas. So if we put so here's a bag, and we put in 5 balls, 3 are red, and 2 are blue. And then we pick them out one at a time. What's the probability of a particular arrangement of balls? So for example, we could pick them out and we might get a red and a blue and a red. Or we might get blue, red, blue, red, blue. So what's the probability of a particular sequence? So in some order. Well, so there's 5 possibilities for the first ball, and that leaves you only 4 possibilities for the second ball, and there's 3 possibilities. But the order of the red balls doesn't matter. Red ball number 1, and that's 2 and 3. That's not different from 3, 2, 1. So the arrangement of red balls doesn't matter. And so there are 3 factorial ways to arrange the red balls. And there's 2 factorial ways to arrange the blue balls. And we've got something that looks similar to this. So how does this map onto quanta and oscillators, though? I mean, it's not like picking colored balls out of a sack. Well, one way of drawing a diagram involving quanta and oscillators would be to say that if we have 3 oscillators and 4 quanta, we can kind of draw the compartments like this. So we could say we could have one oscillator and then a compartment barrier, and 2 oscillators and a compartment barrier, and then the last oscillator, the last quantum. So this 1 quantum in the first oscillator, 2 quanta in the second oscillator, 1 in the third. Or we could say we could put all 4 in the first, and then we'd have an arrangement like that. Or we could have 1 and 3 and 0. And so this looks like red balls and blue balls. So if we consider these barriers to be objects that we can rearrange in between, then in fact, and notice that we have 2 barriers for 3 oscillators. So that's where the n-1 comes from. So omega is the number of quanta plus the number of barriers, if you like, divided by the fact that it doesn't matter which quantum goes in which compartment, and it doesn't matter which barriers where. Yes?
Why would we include the barriers?
This is, okay, so why would we include the barriers? This is really a little bit of an abstract mathematical mapping of this problem onto that problem. Okay, so we're abstracting up at a representation saying, if we think about it abstractly, these barriers actually look like the blue balls. I mean, we drew them as a line, as a barrier, but it's a thing. And considering that moving the quanta relative to the barrier looks a lot like that rearrangement, the math ought to be the same. So it's a way of arguing that the mathematics ought to be the same. Okay. So we now have an equation for finding the number of ways. Let's put this up here. The number of ways of arranging Q quanta of energy among n oscillators. Okay. So now what we want to think about is this issue of energy, the most probable energy distribution between 2 objects that may start out with different energies. So we're back to the block of iron and the block of aluminum coming together. And so in this situation, the macrostates would be, the macrostate would be the amount, the object, the amount of energy in one block at equilibrium. And the microstate is all the different ways that energy could be arranged within that block. Okay. So, so let's think about the following situation. We have 2 objects, and the total energy we have to distribute between these 2 objects is E, which is E1 plus E2. So block 1 has E1, and block 2 has energy E2. And there are, for this block, there are 10 ways to arrange this energy in this block. It's a very small particle, okay, in this block. And so that's omega 1. For omega 2, there are 15 ways to arrange that energy E2 in that block. How many ways are there to arrange the energy as a whole, keeping 10 quanta and keeping this much energy here and that much energy here. So how do we think about this? We could think about a simpler situation that's more concrete. So let's say we think about two atoms where we've got and there's 2 quanta of energy in this atom and 1 quantum of energy in this atom. So how many ways are there of doing this? Well, for this atom, we could have 2 0 0 0 2 0 0 0 2 1 1. So I think there's 6 ways, right? But for every way to arrange these 2 quanta here, we could have this 1 quantum here, or we could have it here, or we could have it here. So if we pick this arrangement, there are 3 ways to arrange this energy here. If we pick this arrangement, there are 3 ways to arrange this energy here. We pick this arrangement, there's still 3 ways to arrange this energy here. So the total number of ways to arrange energy looks like the product of the number of ways. So omega total is omega 1 times omega 2, 6 times 3, which would be 18 ways to, so 18 possible microstates here. So what's the story here? Yeah, it's 4, isn't it? So we have 10 ways. So omega total is omega 1 times omega 2, which is 10 times 15, which is 150 ways to possible ways to arrange the energy. So this macro state is energy E1 here and energy E2 here. A different macro state would be energy E3 here and energy E4 here. And it turns out that the most probable macro state, the most probable amount of energy here and here, is that macro state that's got the most ways of arranging the energy inside the most microstates that correspond to it. So the energy can be randomized the most. So let's get quantitative about this by writing a program to model it. So we'll write a program called microstates, and we'll make it big. And we're going to make a graph, okay? So And we'll make it a histogram. So we'll make a graph. So we're going to take the total number of oscillators is going to be, let's say, 50, which doesn't correspond to an even number of atoms, but that's okay. And the total number of, and we're going to have two blocks that are in contact with each other. And the first block has, well, let's make this 60. We'll make this one 50. And whatever's in this second block is the total number of oscillators minus the number of oscillators in the first block. That would probably be helpful. And the total number of quanta we're going to put in, we'll start with like 40. And the number of quanta in block 1 will start out at 0. So what we're going to do is just try different partitions of energy. We're going to say, well, we're not going to put any energy in this block. How many ways are there of arranging all the energy in this block? Now we put a little bit here. How many ways are there arranging the energy between these two blocks? So that's the program I want to write. So we'll say while Q1 is less than Q total, Q2 is going to be Q total minus Q1. And the ways, so omega 1, number of ways of arranging energy in the first block, is this combin function Q1 plus N1 minus 1 and Q1. So the way this combin function works is it takes this is the first argument, and then that is the second, and that falls out by default. So we're making, so that's our calculation. And omega 2, the ways of arranging the amount of energy we've got in block 2, should be Q2 plus N2 minus 1 Q2. Q2. Thank you. And and the total weight number is then going to be the product of omega 1 and omega 2, right? And now we should plot it. So omega graph plot. We have to plot it so Q1 and Q2 are related by adding up to Q total. So let's plot against Q1 for the x-axis and omega total on the y, and then we're just going to update Q1 here. So that's just going to pick a way of arranging the energy, calculate the number of possible microstates. What? Yes?
And the while means Q1 less than Q2.
It does, but it would have told me that. Okay, so is that clear what that's supposed to do? So let's see if we made any typos, any other typos. Yep. Needs to be capitalized. Okay, what else have I done? Oh. So let's go back and look at what we did. We have n total is 60, and n1 is a really big block. Okay, N1 has 50 of those 60 oscillators. So block 1 has 50 of those 60 oscillators. Block 2 only has 10 oscillators, so it's really small. And so this is telling us that the way of, here are the ways of arranging the energy so that all of the energies in block 1, so this means, sorry, Q1 is 0, so, and over here we're getting to Q1, the amount of energy in block 1 is really large. So here it corresponds to all the energy in block 2, which is a tiny block, and there aren't very many ways to arrange the energy. And over here it corresponds to all the energy in the big block, and there's a lot of ways. And there's one distribution of energy that seems to be there are a lot more microstates available. So that actually ends up being the most probable. Let's just change the size of the blocks. What do you think should happen if we made them equal number of oscillators? So what should this graph look like? Okay, not a big surprise. Blocks are equal size. Most probable distribution seems to be equal amounts of energy in each block. What if we add more energy? We leave the distribution the same, but we make the total number of quanta 60 instead of whatever it was, 40. Still the most probable distribution, just if we make block 1 really small, then it's more probable that most of the energy is in block 2. Okay, so this is making sense, right? Okay. Now, when we get up to lots and lots of energy, and we are actually pretty much almost there now, so we'll make it 700 oscillators with 100 in block 1 and 100 quanta. Okay, the bigger our system gets, the more sharply peaked this graph gets. And in fact, it's sort of impossible to get any real numbers off of here. So one thing we could do to sort of resolve this a little bit better is just to plot logs, because we'll reduce the dynamic range of things. So so let's actually do this a little bit differently. We'll copy our program here and make a new one. And instead of a histogram, I just want a curve, a graphic curve. And let's see, I want S1, I want to graph 3 things, S2, and S. So we want to plot 3 curves. And here I'm going to say that S1 is just the log of omega 1. In Python, log is the natural log. So what we're doing is we're taking a natural log here. To take a base 10 log, you have to type log 10. So we're taking a natural log here. And S2 is the log of omega 2. And S total is the log of and so let's plot these things. So we're doing Q1, S1, S2 graph. Sorry, I should make this big. Q2, S2, and S graph. We better call that S total graph here. We're going to get into trouble. Yep. No, we're going to plot it all versus Q1 because we all want it to have the same axis. Wait, line what?
Line 4, you're going to spin down or S total.
Okay. Does that look like it might work?
Line 20 needs Q2.
Next one you have a whole dozen people working on this.
Wait, which line is 20? Here in this line?
It should be Q2, right?
No, it shouldn't be Q2 because we're plotting it. Remember, we're plotting. Our graph is versus Q1 goes from 0 to Q total. And that means Q2 goes from Q total to 0 the other way. We're going to plot it on the same axis. Okay? Otherwise it gets confusing. So let's see where the typos are here. Stunning. Okay, so this is a plot of the log of omega. And so the red, for a situation where, let's find out how many oscillators we've got here. We've got 700 oscillators, N1 has 100. So block 1 has 100, block 2 has 600. And so this is the log of the ways of distributing energy in block 2. This is the log of the ways of distributing energy in block 1. This is the log of the total number of ways of distributing energy. And you see that there's a clear maximum here. So that's the most probable situation. Now what have we plotted? We've actually plotted entropy, because the definition of entropy is a constant, which is called the Boltzmann constant, times the log of the number of possible ways of arranging energy. So what we have modulo this constant, what we've actually calculated and plotted is the entropy of block 1 versus the amount of energy in block 1, the entropy of block 2 and versus the amount of energy in block 1, and the total entropy. And we see that there's a maximum at the most probable distribution of energy. So next time we'll come back to this and see what we can do with it.